Hello viewers, welcome to online course on Mathematics 3. This course basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the normal subgroup and quotient group in the chapter of Introduction of Group Theory. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID. Before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture we have discussed about the Quotient and Lagrange's theorem in the chapter of Introduction of Group of module Algebraic Structure. So in this lecture we have discussed about the definition of quotient, and after that we have talked about some theorem on quotient, and after that we have defined the Lagrange's theorem or the statement and the proof of the Lagrange's theorem, and some related examples on quotient as well as Lagrange's theorem we have discussed in previous class. So today we are going to discuss about the normal subgroup and quotient group. So this part is on the first chapter of algebraic structure, and that means the introduction of group theory. Okay, that is the normal subgroup and the quotient group are in the chapter of introduction of group theory in the module of algebraic structure. So here is the content of today's lecture. At first we will discuss about the definition of normal subgroup, and after that we will talk about the theorem on normal subgroup, then and some related examples on normal subgroup we will discuss in lecture 6, and this is my 6th lecture on the module algebraic structure. And after that we will talk about the quotient group, and then we will study on the properties of the quotient group as well, and some related examples we will discuss in this lecture. So at first we will begin with the definition of a normal subgroup. So here is the definition. A subgroup H of a group G is said to be a normal if AH is equal to HA. So here H is the left coset of H in G and H is the right coset of H in G. That means if left coset and right coset both are equal, then it is called a normal subgroup. Okay, where H is the subgroup of G for all A belongs to G. Then in symbol we can write the normal subgroup H delta G. So H is a normal subgroup of the group G and is defined as AH is equal to HA for all A belongs to G. So there are some notes on the normal subgroup. So the first note, it will be AH is equal to HA. Does not implies that AH is equal to HA, where H is the element of capital H, and capital H is the subset of capital G, as well as a capital H is a subgroup of G. So AH is equal to HA, that is the left coset and the right coset, they are equal, and does not implies AH is equal to HA for all H belongs to G. But from the definition of a normal subgroup, it follows that every subgroup of a commutative group is a normal subgroup. Okay, this is the properties of a normal subgroup. And the second note, it will be every group G has at least two normal subgroups, and they are namely G itself and E, where E is the identity element. So these are called the improper or the trivial normal subgroup, and all other are called the proper normal subgroup. Okay, that means in a group G there are two normal subgroup at least, G itself and E. Okay, and these two normal subgroup are trivial. And after that we will take the third note on normal subgroup. For normal subgroup, left coset and the right coset are same. Okay, so in that case this is actually the definition of a normal subgroup. So if left coset and right coset are same, then it is called a normal subgroup for all A belongs to G. And after that we will define the simple group. Okay, so here is the definition of a simple group. A group having no proper normal subgroup is called a simple group. And you know, in a group G there are at least two normal subgroup, and they are G itself and E, and these two subgroup are the improper or trivial subgroup of G, that means trivial normal subgroup of G. But in a simple group there is no proper normal subgroup, and by Lagrange's theorem every group of prime order has no proper subgroup. Hence every group of prime order is simple. So for example, order of G is equal to say 7. So the order of G is a prime, so it is not a simple group. And after that we will discuss some related theorem on normal subgroup. So that is the first theorem on normal subgroup. Let H be a subgroup of a group G, then H is normal in G if and only if XH X inverse it is belongs to capital H, where capital H is a subgroup of G, and for all X is belongs to G. This is the first theorem on normal sub. So here is the proof of the above theorem. Let H be a normal subgroup of G. So we shall prove that XH X inverse it is belongs to H for all X belongs to G. So if H be a normal subgroup of G, then by the definition of a normal subgroup, XH is equal to HX for all X belongs to G. This is the definition of a normal subgroup. So now let H be an element and it is belongs to capital H, then XH is equal to H1X for some H1 is belongs to H. This is the one of the properties of the quotient. Okay, so XH is equal to H1X, where H1 is the element of capital H. Now operate X inverse on the both side. On right we get XH X inverse it is equals to H1 into XX inverse, and you know that G be a group and H is a subgroup, so it satisfies the inverse property as well. So therefore X into X inverse it is belongs to G and it is equals to E, where E is the identity element. Okay, so H X inverse it is equals to H1 into E, that is H1, and H1 is the element, it is belongs to capital H, so XH X inverse it is belongs to capital H. Okay, and next let XH X inverse it is belongs to capital H for all H belongs to H and for all X belongs to G. So we shall prove that H is a normal subgroup of G from this. Now let A is belongs to HX. So therefore A is equals to H2X for some H2 is belongs to H. So this is the definition of the quotient, you know that. So therefore the above equation implies X inverse into H2X, where X inverse is equal to identity, you know that. So therefore H2X can be written as X inverse into H2X, where X inverse is equal to identity, you know that. And applying the associative properties, then from this we'll get X into X inverse H2 into X inverse of inverse, and you know that X inverse of inverse is equal to X. So X inverse into H2X, and it can be written as X into X inverse H2 X inverse of inverse. And you know that X inverse H2 X inverse of inverse, it is equals to H3. That is given. X inverse is equal to belongs to H, and you know that X inverse is equals to sum H, which belongs to capital H. So that means, so in that case, X inverse H2 X inverse of inverse, it is equals to say H3, okay, and H3 is belongs to H as well, where X inverse is belongs to G, and you know that X is belongs to G, so X inverse is also belongs to G, as G is a group, so inverse property is also satisfied. So therefore, if A is belongs to Hx, and this imply A is belongs to Xh. So you know that Xh, it is belongs to X into capital H, where X3 is the element which is belongs to capital H. So therefore, from the above, we get Hx is a subset of Hh, and you can write it equation number 3. Next, let B be the element, and it is belongs to Xh. Okay, so from this we'll get B is equal to Xh4 for some H4 is belongs to capital H, and H4 is the element, and it is belongs to capital H, and B is equal to Xh4. Then the above equation, it can be written as Xh4 into X inverse X, and you know that X inverse X, it is equals to identity. So H4 can be written as this, Xh4 X inverse into X, and applying the associative property on the group, so this equals to Xh4 X inverse into X. Okay, and you know that Xh4 X inverse, it is belongs to capital H. Okay, so it can be written as H5, and H5 is equal to Xh4 X inverse, and it is belongs to H. So this is equals to H5 into X. Okay, so B is belongs to Xh, and it is implies B is belongs to Hx, where H5 it is belongs to H, that is H5 into X, it is belongs to Hx. Okay, so from the above we conclude that Hh is a subset of Hx, and we can write it equation number 2. So in virtue of equation 1 and equation 2, we have Xh is equal to Hx for all X is belongs to G. Hence, H is a normal subgroup in G. So you know this is the definition of a normal subgroup. Xh is equal to Hx for all X belongs to G. So H is a normal subgroup in G. Hence the proof of the first theorem on normal subgroup. So after that we'll take the second theorem. So this is the second theorem. A subgroup H of a group G is normal if and only if Xh X inverse it is equals to H for all X belongs to G. So here is the proof of the above theorem. Let H be a normal subgroup of G, then Xh is equal to Hx for all X belongs to G. This is the definition of a normal subgroup. So from this we shall prove that Xh X inverse it is equals to X for all X belongs to G. So now from the above equation, that means Xh is equal to Hx. Now operate X inverse on the right of the above equation, we get Xh X inverse, and it is equals to H into X inverse. Okay, and you know that X be the element in G and G be a group, so X inverse it is equals to identity. Okay, so Xh X inverse it is equals to H into E, and E is also belongs to G, and H is equal to H. So hence the proof of the necessary part, or the first part of the above theorem. So now let Xh X inverse it is equals to H for all X belongs to G. Then from this we will prove that H is a normal subgroup of G. That means Hx is equal to Xh. So therefore the above equation, that means Xh X inverse is equal to H. Then from this we will get Xh X inverse into X is equal to Hx. So in that case, where operate x on the right of the above equation, you get this one. So x inverse into x, it is equals to hx. And you know that x inverse x, it is equals to e, and e is belongs to g. So therefore x into he, it is equals to hx. That means xh is equal to hx for all x belongs to g. So hence H is a normal subgroup of G. So hence the proof of the sufficient part of the above theorem. So after that we will take third theorem on the normal subgroup. A subgroup H of a group G is normal of G if and only if each left coset of H in G is the right coset of H in G. So here is the proof of the above theorem. Let H be a normal subgroup of G, and then AH is equal to HG for all A belongs to G. This is the definition of the normal subgroup. Okay. So each left coset of H in G is a right coset of H in G. So from the definition of normal subgroup, we can easily conclude that left coset and right coset both are equal. That means each left coset of H in G is equals to the right coset of H in G. Now let each left coset of H in G is a right coset of H in G and A be any element of G. Then AH is equal to BH for some B belongs to G. Then from this we will prove that AH is equal to HG. That means HB it is equals to HA for some B belongs to G. Since E be the element and it belongs to H, and you know that H is a subgroup of G, so H itself is a group. So E be the identity element is belongs to H. So A into E it is also belongs to AH. This is the left coset of H in G. That is A is belongs to AH. So therefore you know that AH is equal to HB. Therefore A is also belongs to HB. So therefore A is equals to H1B. So in that case, where H1B any element and it belongs to capital H. So from this we will get AB inverse it is equals to H1. Okay, and can write it equation number 1. So now we shall show that HB is equal to HA. So now let X is the element, it is belongs to HB. Therefore X is equal to H to B for some H2 in H. This is the definition of the coset. Or the above equation can be written as X is equal to H2 H1 inverse into H1 into B, where H1 inverse into H1 is equal to identity. So this term can be written as this H2 into H1 inverse into H1 is equal to B. That means H1 inverse into H1 it is equals to identity. So from this we'll get H2 into H1 inverse into, and you know that H1 it is equals to, I have already found this one, H1 is equal to AB inverse. Okay, so putting this value in that section we'll get H2 into H1 inverse into AB inverse into B. And you know that B inverse of B it is equals to identity. So X is equals to H2 into H1 inverse into A. And while H2 into H1 inverse it is belongs to H. And say H3 is equal to H2 into H1 inverse. So and it is belongs to capital H, as H is a subgroup of G. So therefore X is equals to H3 into A. So from this we conclude that X is belongs to H into A. So thus HB is a subset of HA. Now let Y be an element and it is belongs to HA. Then Y is equals to H3 into A for some H3 is belongs to H. So this can be written as this. Okay. And again the above equation can be reduced to y is equal to h3 into h1 into h1 inverse into a, and you know that h1 into h1 inverse it is equals to identity, so we can write h3 of a as h3 into h1 into h1 inverse of a, and you know that h1 it is equals to ab inverse. Okay, so I have already found this one, h1 is equal to ab inverse. Okay, and now putting this value h1 is equal to ab inverse in the second part of h1, then from the above equation we have h3 into h1 into ab inverse whole inverse into a using the equation 1. So therefore y is equal to h3 into h1 into, and you know that ab inverse of inverse it is equals to b inverse of inverse into a inverse, but b inverse of inverse is equal to b into a inverse into a, where you know that a inverse into a is equals to identity. So y is equal to, after simplifying this we get h3 into h1 into b, and where we consider h3 into h1 it is equals to h4, and it is also belongs to h. So therefore y is equal to h4 into b. So from this we get y is equal to h4b, where h4 is belongs to h, and this implies y belongs to h into b, thus ha is subset of hb. So from this, that means hb subset ha as well as ha is subset of hb. So from these two we conclude that hb is equal to ha. So therefore ah is equal to hb. After putting the value of hb is equal to h in the above, we get ha is equal to hb. So therefore h is a normal subgroup of a group is a normal subgroup. This is the proof of the third theorem on normal subgroup. So after that we'll take the fourth theorem. So it is the intersection of any two normal subgroup of a group is a normal subgroup. This is the theorem, and here is the proof of the above theorem. Let h1 and h2 be two normal subgroup of a group G. Okay, so here h1 and h2 normal subgroup, we consider that, and then h1 intersection h2 it is a subgroup of G, as h1 and h2 are the subgroup of G. So h1 intersection h2 is a subgroup of G. This is the theorem on the subgroup. Okay, intersection of any two subgroup it is a subgroup, and I have already proved this theorem in the lecture of subgroup. Now let x be any element of G and h be an element it is belongs to h1 intersection h2. So if h is belongs to h1 intersection h2, then from this we'll get h is belongs to h1 and h is belongs to h2. And you know that h1 and h2 both are the normal subgroup of G. Then from the properties of a normal subgroup, or from the first theorem on a normal subgroup, we have x h x inverse, and it is belongs to h1, as well as x h x inverse it is belongs to h2, where h1 and h2 are the normal subgroup of G. So if x h x inverse is belongs to h1, x h x inverse is belongs to h2, then from this we conclude that x h x inverse it is belongs to h1 intersection h2. So therefore x is belongs to G and h is belongs to h1 intersection h2, and combining these two we'll get x h x inverse it is belongs to h1 intersection h2. This is the one of the properties of a normal subgroup. So from this we get h1 intersection h2 is a normal subgroup of G. So from this we conclude that the intersection of any collection of a normal subgroup of a group is a normal subgroup of G. This is the fourth theorem of normal subgroup. After that we will discuss some related examples on normal subgroup. So here is the example. This is the first example. So that every subgroup of a cyclic group is normal. Here is the solution. Let G be a cyclic group and H be a subgroup of G, and let X is belongs to G and H is belongs to H. Then X H X inverse, and this can be written as X X inverse into H. And you know that G be a cyclic group and it is given, so G is abelian. That means H x inverse, it is equals to x inverse H. So therefore x H x inverse, it can be written as x inverse into H. And you know that x inverse, it is equals to identity because G is a group. So x inverse is equal to identity, and it is also belongs to G. So therefore x inverse, it is equals to H, and H is the lies in capital H, where capital H is a subgroup of G. So therefore x is belongs to G and H is belongs to H, and this imply x inverse, it is belongs to capital H. Then from the first theorem on normal subgroup, we conclude that H is a normal subgroup of G. Now we'll take the second example on the normal subgroup. Here is the example. Let G be a group and H be a subgroup of index 2 in G. Then prove that H is a normal subgroup of G. So here is the solution of the above examples. Since the index of H in G is 2, so there are only two distinct left coset or right coset of H in G, and the two distinct left coset, and they are H and G minus H. Okay, these two are the distinct left coset. So now let X is belongs to H, and then X H, it is equals to H, as well as Hx is equal to H. Then from this we'll get Xh is equal to Hx. And next, let X is not belongs to H, that means does not belongs to H, then X is belongs to G minus H, where G minus H is distinct from H. So if X does not belongs to H, then it is belongs to G minus H. So therefore Xh, it is equals to G minus H, as G minus H is only the left coset, as well as Hx, it is equals to G minus H, where G minus H is only the right coset. So combining these two, we conclude that Xh, it is equals to Hx for all x belongs to G. So therefore H is a normal subgroup of G. So now move on the third example on the normal subgroup. So that the center of G given by Zg, and Zg is equal to A belongs to G, such that Ag is equal to Ga for all G belongs to G, is a normal subgroup of G. That is the solution of the above example. We have already proved in the previous example that Zg is a subgroup of G. So for any G is belongs to G, and for any A is belongs to Zg, where Zg is the center of a G, and you know that Ga, it is equals to Ag. Okay, applying the above relation, we'll get this one. And you know G inverse, it is equals to E, where G is the element in G and G is the group. So therefore G inverse, it is equals to A into E, and A into E is equal to A, and A is belongs to Zg. So G inverse, it is belongs to Zg. Then from the first theorem on normal subgroup, we conclude that Zg is a normal subgroup of G. Or if G belongs to G, A belongs to Zg, and from this we get G inverse, it is belongs to Zg. That is Zg is a normal subgroup of G. Now we are going to take one more examples on the normal subgroup. So here is the example. If H is a subgroup of G and N be a normal subgroup of G, then so that H intersection N, it is a normal subgroup of H. Is the solution. Since H and N are the subgroup of G, so H intersection N is also a subgroup of G. This is the one of the properties of a subgroup. So if two subgroup, the intersection of any two subgroup is a subgroup. So that means H intersection N is a subgroup. But H intersection N, it is a subset of H. So therefore H intersection N is a subgroup of H. So now let X be any element, it is belongs to H, and H be any element, it is belongs to H intersection N. So if H is belongs to H intersection N, then from this we get H is belongs to H and H is belongs to N. So X inverse, it is also belongs to N, as N is a normal subgroup of G. So also x is belongs to H and H is belongs to H, and this imply x H x inverse it is belongs to H, as H is a subgroup of G. So hence x H x inverse it is belongs to H intersection N for all x belongs to N and H belongs to H intersection N. So consequently H intersection N is a normal subgroup of H. Now move on the next slide. So in this slide we will take one more example on the normal subgroup. Prove that the normal subgroup of a group G is commutative with every non-empty subset of G. Okay, so here is the solution. Let K be a normal subgroup and H be a non-empty subset of G. So we now prove that KH is equal to HK. So now let HK, it is belongs to HK, capital HK, where K is the element, it is belongs to K, and H is the element, it is belongs to H. So then KH, it is equals to HH inverse into KH. So we can write this one as HH inverse into KH. Okay, now applying the associative property on that, we get H into H inverse K into H inverse of inverse. Okay, so we can write H as H inverse of inverse. So therefore from this we get KH is equal to H into K1, and we know that H inverse of KH inverse of inverse it is equals to K1, and it is also belongs to K. So therefore KH is belongs to HK, where HK1 it is belongs to HK. So therefore KH is a subset of HK, and we can write it equation number 1. Again let H2 K2 and it belongs to HK, where H2 is belongs to H and K2 belongs to K. Then H2 K2 can be written as H2 K2 into H2 inverse into H2, and where H2 inverse into H2 it is equals to identity. You know that. So applying same thing, we have H2 into K2 into H2 inverse into H2, where H2 K2 H2 inverse it is equals to K3. Okay, so and it is also belongs to K. So therefore H2 K2 and it is belongs to KH, where you know K3 into H3 it is belongs to KH. So therefore HK is a subset of KH, and we can write it equation number 2. So from equation 1 and 2 we conclude that KH is equal to HK. This is the proof of the 5th example on the normal subgroup. Now move on the second part of this lecture, and this is actually the quotient group. So here is the definition. Let H be a normal subgroup of G, then there is no distinction between left and right coset of H in G. Let G slash H be the collection of all coset of H in G. We shall now show that the set G slash H form a group with respect to the operation of coset defined by AH into BH is equal to AB into H for all AB belongs to G. So here is the theorem on the coset. The set G slash H, and it is actually the collection of all coset of H in G, and they are H, BH, okay, and this is defined as this H, BH is equal to ABH for all AB belongs to G. So the set G slash H of all coset of a normal subgroup H in G is a group with respect to the operation defined by H, BH is equal to ABH for all AB belongs to G. So from this we shall prove that G slash H satisfied closure property, associative property, identity property, and inverse property. So here is the proof of the above theorem. Here G slash H is equal to AH such that A is belongs to G. Now let ABC be 3 elements, and they are belongs to G, so that AH, BH, and CH are all belongs to G slash H. Okay, so then AH into BH and it is equals to, you know that ABH and it is given and it is belongs to G slash H, as A comma B is belongs to G. So and this imply AB belongs to G. So G slash H is closed. Now move on the second property, and here is the second property of the above theorem. Now AH into BH into CH, where BH into CH within third bracket, and it is equals to AH, and applying the above relation in the third bracket we will get BC into H. Okay, so AH into BH into CH, it is equals to AH into BC into H. And again applying the above relation we get A B into C into H. And you know that G is the group, so it satisfies the closure property as well as associative property. So A into BC, it is equals to, you know that, AB into C. And from this we will get AB into H into CH. That is, and ABH, it is equals to, you know that, AH into BH within third bracket into CH. Thus the operation multiplication in G slash H is associative. Now let us move on the next property, and there is a third property. We have H is equal to E into H, and it belongs to G slash H. Then H into AH, it is equals to EH into H. And applying the above relation we will get E into A into H, it is equals to A into H. That is, H into H, it is equals to H, and similarly we will find AH into H, it is equal to AH. So hence H is the identity element of G slash H. Now move on the fourth property of the above theorem. As A is belongs to G, implies A inverse, it is also belongs to G. You know that G is the group, so its inverse is also belongs to G. So AH, it is belongs to G slash H. So this implies A inverse of H, it is also belongs to G slash H. So now AH into A inverse H, it is equals to, you know that, from the given relation we will get A inverse into H, and you know that A inverse, it is equals to identity. So AH into A inverse H, it is equals to EH, and EH is equal to H. As well as A inverse into H into AH, it is equals to, and similarly from this we will get A inverse A into H, it is equals to H. So the quotient A inverse H is the inverse of AH. Okay, so AH whole inverse, it is equals to A inverse H. This is the inverse property of G slash H. Thus the inverse of each element of G slash H exists. Hence G slash H satisfy the following four properties, that means closure property, associative property, identity property, and the inverse property. Hence it is a group. That means G slash H is a group. So after that we will take the second theorem on the quotient group. Every quotient group of an abelian group is abelian. So let H be a subgroup of an abelian group G, and then H is a normal subgroup of G. So the quotient group G slash H, it is exist. Okay, so in that case where H is a normal subgroup of G. And now let AB be two elements and it is belongs to G. So then AH and BH, both the elements are in G slash H. So from this we shall prove that G slash H is an abelian group. So now AH into BH, and from the definition of quotient group, and it is equals to, you know that, AB into H. And G is an abelian group, so AB is equal to BA for all AB belongs to G. So therefore AB into H, it can be written as B into H, and B into H, it is equals to, from the definition of quotient group, BH into H. So therefore AH into BH, it is equals to BH for all AH into, for all AH comma BH, it is belongs to G slash H. So hence the quotient group G slash H, it is abelian, where G is the abelian group. But the converse part of the above theorem, it is not true. For example, let G is equal to S3, and S3 is the symmetric group of order 6, and H is equal to A3, and A3 is the alternative group of order 3. Then the quotient group S3 by A3 of index 2. So you know that the order of S3 is equal to 6 and order of A3 is equal to 3. So the index of S3 by A3, that means the quotient group S3 by A3 and is equals to 2. So it is abelian by the Lagrange's theorem. As every group of order 2 is abelian, you know that. So but the symmetric group S3 is not a abelian group. So the converse part of the above theorem is not true. Now let us move on the next slide. So in this slide we will discuss the third theorem on the quotient group. So every quotient group of a cyclic group is cyclic, but the converse part is not true. So let H be a subgroup of a cyclic group G, then H is a normal subgroup of G. So as G is a abelian, so the quotient group G slash H exists. And let A be a generator of G. So G be the cyclic group, so there is a generator and it is equal to say A. Then A to the power n, it is belongs to G for some integer n. Therefore, A to the power H and it is also belongs to G slash H. That is in the quotient group. Okay. So therefore, A to the power n into H, and it can be written as A into up to n factors into H. And applying the quotient group, we get AH into AH and up to n factor. That means AH whole to the power n. So therefore, G slash H is a cyclic group and AH is a generator of it. That means AH belongs to the power n, that is belongs to G slash H. That's why G slash H is a generator of the quotient group G slash H, and it is a cyclic group as well. And the converse part of the above theorem is not true. For example, let G be the symmetric group of order 6, that means S3, and H be the alternative group of order 3, that means A3. Then the quotient group S3 by A3 is of order 2, and hence it is cyclic. As every group of prime order is cyclic, you know that. But the symmetric group S3 is not a cyclic group. So the converse part of the above theorem is not true. So after that we will take an example on the quotient group. So here is the example. Let Z be the center of a group, and if G slash H is a cyclic, then prove that G is abelian. So here is the solution. Since G slash H is a cyclic group, then let there is a generator, so G slash H, it is equals to generator of GZ for some G belongs to capital G. And let A be any element is belongs to G, then AZ it is belongs to the quotient group G slash H. So therefore AZ is equal to GZ whole to the power m for some integer m. I know that G slash H, in that case it is a cyclic group. So GZ whole to the power m can be written as GZ into GZ and up to m factors. And applying the quotient group, we get G into up to m factors into Z, that is G to the power m into Z. So therefore A is belongs to G to the power m into Z, implies A is equal to G to the power m into Z1 for some Z1 is belongs to Z, where Z1 be any elements in capital Z, and Z is the center of a group. And now let B be any element, it is belongs to G. Then similarly we will get B is equal to G to the power n into Z2 for some Z2 belongs to Z. Now from this we shall prove that G is abelian. That means AB is equal to BA. So therefore AB is equal to, in that case where A is equal to G to the power m into Z1 and B is equal to G to the power n into Z2. So from this we will get G to the power m into Z1 into G to the power n into Z2. And you know that Z1 is lies in capital Z, that is in the center of a Z. So G to the power m Z1 G to the power n Z2, and can be written as G to the power m into G to the power n into Z1 Z2. As well as Z2 is a point on the center of a group, so it can be written as G to the power m plus n into Z2 into Z1. Then from this we get G to the power n plus m into Z2 into Z1. That means g to the power n into g to the power m, and we know that g to the power n plus m, it is equals to g to the power n into g to the power n into z2 into z1, and from this we will get g to the power n into z2 into g to the power m into z1. So and you know that g to the power n into z2 it is equals to b, and g to the power m into z1 it is equals to a. So therefore ab is equal to ba. So thus ab is equal to ba for all ab belongs to g, hence g is abelian. Hence the proof of the first example of quotient group. So I will stop here today's lecture. Thank you.